Hi, everybody, and welcome to today's edition of the Spectral Geometry in the Clouds seminar. Today, we have the pleasure of having Jean-Claude Cuenin from Loughborough University, who will talk to us about Schrödinger operators with complex potentials beyond the Laptev-Safronov conjecture. As usual, if you have questions, you can ask them in chat, and we will relay them during the talk, where you can simply unmute yourself and ask your question directly. And this is it. So, Jean-Claude, the floor is yours.
Thank you very much, Sean, for the introduction, and thanks for the invitation to speak in this very nice seminar. So it's been a pleasure to watch the talks on YouTube. I have teaching around this time, but I watch most of the talks. So anyway, this talk is going to be about Schrödinger operators with complex potentials, and maybe you have seen the talk of Sabine B in the same seminar series. So this is going to be sort of a continuation of that talk, but I will recall everything that we need. So no worries if you haven't seen that. And also maybe I've seen a similar talk of Rupert Frank in a different seminar series. And so there are many intersections, but I try to give a bit different emphasis and perspectives here. All right, but so let's start from scratch. So we consider a Schrödinger operator on L2 of Rd. Usually D is bigger than 1, but d equal 1 is also allowed. And we are interested in complex valued potentials, so operators with complex valued potentials. And so we assume that the potential is in LQ for some Q less than infinity. So we are looking at potentials that decay in a certain average sense at infinity. And for the purpose of this talk, let's also assume, just for technical simplicity, that V is bounded. This is not important, but it just makes talking about the operator easier. So we don't need to talk about domains and so on. It's just this operator is defined on the domain of the Laplacian, which is the second order Sobolev space. Okay, and the spectrum of the Schrödinger operator is just a positive half line together with a set of, in this case, complex eigenvalues. They have finite algebraic multiplicities, and the only possible accumulation points lie on this half line on the essential spectrum. So we distinguish here between algebraic and geometric multiplicities, but this will not play a big role in the rest of the talk. It's just because the operator is no longer self-adjoint, there's a sort of a difference here. Okay, and we are interested in quantitative bounds on these eigenvalues. So we want to know where they live, and so I will focus basically on bounds on individual eigenvalues. There are also interesting questions about sums of powers of eigenvalues or about the number of eigenvalues, but in this talk I will focus on individual eigenvalues. All right, so let's start with well-known results about real potentials. So these are classical results going back to Keller in the 60s and Lieb and Tiring in the 70s, which say that you can bound power of an eigenvalue to the power gamma by an integral of the potential to the power gamma plus half the dimension. Okay, so sometimes in this talk I will also write this as Q. Okay. And so this inequality is true for real potentials for any gamma bigger or equal than a half in one dimension, and for any gamma bigger than 0 in higher dimensions. And for complex potentials, there was a conjecture of Laptev and Safronov from 2009, where they recognized that for complex potentials, this range might actually be smaller than for real potentials. So they conjectured that this inequality should be true for gamma in some interval, so between 0 and d over 2. And well, it turns out that this is not the correct upper bound, but what is true is that there is an upper bound. So okay, I will talk about this in a minute. But so what they probably have in mind was some sort of radial potentials, and I will later explain that for radial potentials, their conjecture is actually true. All right. And the inequality holds in one dimension and for gamma equal to 1/2. And this is an old result from 2001 by Abramov, Veslanian, and Davis, or in higher dimensions for gamma less or equal than 1/2. And this was proved by Rupert Frank in 2011. Okay, so the remaining question for a long time was, what about this case? So what about higher dimensions and gamma bigger or equal than 1/2? Okay, so here's, well, the statement is that for gamma bigger than 1/2, the conjecture is false. And so this counterexample, we did this together with Sabine B recently this year, and Sabine talked about this in a previous episode of this seminar. So let me just quickly recall how the counterexample is constructed. So you take a long thin tube, right? So a tube with dimensions epsilon inverse, and so epsilon minus 1/2 and epsilon inverse, and you consider a potential that is supported on this tube, or a family of potentials, one for every epsilon, and so this potential will be bounded by a constant times epsilon times this indicator function here, and then you can compute that the LQ norm of this potential when Q is bigger than so if Q is bigger than d plus 1/2, which is equivalent to gamma bigger than 1/2, then the LQ norm of this potential goes to 0 as epsilon goes to 0. Okay, and on the other hand, the absolute value of the eigenvalue is always of order 1, so it's approximately 1. So hence the inequality cannot be true. And as a corollary, so this is an extension of a result that Sabine proved earlier, is that you can actually take this counterexample and just place many copies of it next to each other and sort of separate the copies far enough. And you can prove that you can get eigenvalues that accumulate to every point of the essential spectrum, even though your potential is very nice and very small. So the norm of the potential is less than any number you wish. So delta is, given delta, there is a potential such that the norm is less than delta, and such that any point in the essential spectrum is an accumulation point of minus Laplace plus v. Okay, so this is quite a straightforward consequence of this construction here. And then, so there is also a quantitative version that I'd like to mention here. So this corollary can be made more quantitative. You can actually say, so you can choose your sequence that you want to, right? So in this picture, so you can choose the sequence accumulating to the essential spectrum as long as it satisfies a certain condition, like here. Then you can construct a potential with the following properties. So first of all, so for any n, there is a discrete eigenvalue set n, and this eigenvalue is exponentially close to the zeta n, and the zeta n is the sequence that is given. Exponentially close in the sense that, given any constant here c, I can make this less than e to the minus imaginary part of zeta n to the minus c, and you can see that the imaginary part of zeta n has to go to 0 because of this summability condition, and hence this is a exponential smallness condition here. So you should maybe think about this, the following situation. So think about the case where you basically have a strip here. So say this is between 1/2 and 3/2, and you look at eigenvalues accumulating in this strip, and then you can forget about this guy here. So it's a bit simpler. All right, and then the potential again is bounded by delta. so possibly up to a constant, but I didn't write this here. And also what is sort of not contained in the previous corollary is that not only is the potential in some in some LQ, but it actually decays pointwise. So there exists a beta, and you can actually compute this beta. So it depends on all the constants that pop up here. There exists some beta bigger than 0, such that v of x is less than x to the minus beta. Okay. So that's okay. Before I go to that, just let me comment. So maybe you have seen the talk of Martin Vogel about non-self-adjoint Schrödinger operators. In his talk, the Schrödinger operator was sort of very non-self-adjoint because there is some commutator or Poisson bracket condition that ensures that you have sufficient non-self-adjointness. But here in our case, we sort of only look at perturbations of a self-adjoint operator. So the only non-self-adjointness comes from this potential, and the potential is small, right? It's small, and it's also decaying at infinity. So this is sort of very weakly non-self-adjoint, but nevertheless, you can have very unintuitive or very strange phenomena like this, even for this kind of operator. Okay, so now I'd like to make a small detour and discuss some connections to harmonic analysis. So many of you probably know what's called the Sobolev trace lemma, right? You take the Fourier transform of a function and you restrict it to a hypersurface, and so you can always do this in a weighted L2 space. So this weight W epsilon is just some x to the minus a half minus epsilon, and the constant depends on epsilon and s. So you can always do this, and the proof is more or less trivial. You just flatten out the surface locally, and then you apply this trivial bound and Cauchy-Schwarz. That's it. And so you can express this inequality in a bit more abstract way. So you can define an operator. It's called the restriction operator, or Fourier restriction operator. So that does that, take the Fourier transform and restrict to the surface. And then you can compute its adjoint. And the adjoint is just, you take a function, you multiply it by the surface measure, and then you take the Fourier transform. And you can also compute R star R. And R star R is an operator which maps, Rn to Rn. So this operator here maps Rn to a surface, and this operator here maps a surface to Rn, but this one sort of maps the space to itself. It's sort of convenient to work with. Sigma S is the surface measure on S, and you can write this inequality here in a so-called T star T version, or R star R in this case. So this is just the duality argument. Right, so you can write it as this inequality here, where we put the weights left and right of this R star R operator, and then you just get the square of the constant. Okay, and this T star T version or R star R version can also be written in the equivalent form that here in the middle of these weights, you put the imaginary part of the resolvent, and this is just because the imaginary part of the resolvent, right, the difference of these two things, is basically R star R up to a scaling constant lambda to the n minus 1. Okay, so also as a remark, by Stone's formula, R star R is proportional to the spectral measure of square root of minus Laplacian. All right, now we leave this trace lemma and we discuss something related but a little bit more sophisticated, which is the steintomas theorem. And so this requires that the surface has non-zero Gaussian curvature at every point. Okay, so we assume, for example, that the surface is compact, and then at every point we want it to have non-zero Gaussian curvature. And so the theorem says that you can restrict a function in LP, you can restrict it to the surface in L2 if P is this exponent here. And this is the optimal exponent in the sense that it is the largest possible exponent, right? So you can always, by Hölder's inequality, you can always go down, but you cannot go up. So this is the largest possible. And again, you can write down a T star T version of this inequality. And again, this is equivalent to a bound on the spectral measure or on the imaginary part of the resolvent. But there is also a version for the full resolvent, and this follows from a paper of Cuenin and Sock in the 80s. Namely, they established the bound written here. So KRS stands for Cuenin-Sock. So you take the full resolvent and you, so let's write the spectral parameter as lambda squared plus I times 0, which means I take lambda squared plus I epsilon and I let epsilon go to 0. So I look at it's basically a limiting absorption principle. I look at the limiting resolvents, and I can take this limit from above and below, but I will not distinguish between these limits here. So, their inequality says that you can that the resolvent is a map from LP to its dual LP prime if P and P prime satisfy this condition, and so the important condition is this one here, which is basically what happens if you replace P by PD, and you take this difference here, and the upper bound is just sort of the standard Sobolev embedding that you need to respect, because this operator is elliptic of order 2 away from its characteristic set. So the important inequality is this one here. Okay, and the exponent just comes out from scaling. So you can prove this inequality for lambda equal to 1, and then just scale. And so because the steintomas inequality is equivalent to an inequality on the imaginary part of the resolvent, it's clear that an inequality for the full resolvent implies the same inequality for the imaginary part. So Cuenin-Sock implies steintomas, but actually also the other way around is also true. And the same principle holds on any compact Riemannian manifold. So you can have analogs of these two inequalities on compact Riemannian manifolds. I will not discuss this here, but so this has first been observed by these authors here, and then last year I also gave some purely functional analytic argument, which doesn't so basically doesn't use any information about. I mean, this thing here uses what's called the Hadamard parametrics, and so this one here basically only uses a functional analytic argument to show that these inequalities are equivalent. Okay, so let's go back to complex potentials. So the Cuenin-Sock bound has been used in this paper by Rupert Frank in conjunction with what is known as the Bürman-Schwinger principle. So here is the Bürman-Schwinger principle. It's a very convenient and simple device in spectral theory, which says that you can reduce spectral problem to a problem involving only a compact operator. So instead of an unbounded operator, you just consider a compact operator. Right, so Z is an eigenvalue of this operator only if -1 is an operator of this compact operator. So that's a very simple exercise. And therefore, Z is an eigenvalue. So if Z is an eigenvalue, then, well, -1 is an eigenvalue of this guy. So we have the obvious upper bound here. So the norm of this Bürman-Schwinger operator has to be at least 1. And then we just use Hölder here. Right, so we pull out the LQ norm of the potential here. And Hölder gives us this PP prime norm of the resolvent. And the Cuenin-Sock bound tells us how to estimate this. Okay, namely by this power of Z. Okay, so then you just rearrange, you put this on the left-hand side, and you're done. You get this estimate. Okay, and it's true if you do the arithmetic here, if you calculate the restrictions on Q given the restrictions on P for this estimate here, you end up with this condition. Again, I omitted, so you also need to assume that this is bigger than d over 2, but as I said, we are assuming here for simplicity that the potential is bounded, so we are just ignoring these local regularity assumptions here. Okay, and then so this is called the short range case because Q has to be small, and so the complementary case we call the long range case for the purpose of this talk. And if you interpolate this bound with the trivial L2 bound, the L2 bound being just the obvious resolvent bound minus Laplace minus Z inverse from L2 to L2 is less or equal than 1, is actually equal than 1 over the distance of Z to the spectrum. Okay, so if you interpolate with this bound, and this was done in this paper here, then you can prove this estimate. So for Q bigger than d plus 1 over 2, you have to trade some powers of this absolute value of Z for a distance of Z to the spectrum, which of course this thing here is always less or equal than the absolute value of Z, so this inequality is always weaker. It could be weaker except you're in the left half plane, but then it's sort of not so interesting anyway. So all these inequalities are only interesting if you are very close to the positive real axis. So we can always assume that we are in some small sector here around the real axis, positive real axis. Okay, and so for me it was a bit surprising that this inequality is actually sharp. So the counterexample with Sabine also shows that this bound is sharp. So let me say a little bit more about the counterexample. And so first of all, let me also mention that different approaches have been tried. So actually, Frank and Simon had, in a sense, almost disproved the conjecture, but they were able only to consider embedded eigenvalues. So it turns out that the upper bound that you can prove with these harmonic analysis techniques, they can be extended to also hold for embedded eigenvalues, and then you can prove that this is actually best possible. So for embedded eigenvalues, you can construct potentials that violate sort of the analog of this conjecture if you include the case of embedded eigenvalues. And so this construction is based on a previous work by Ionesco and Jerison, who were interested in unique continuation. And then later I gave a general version of this construction, which is applicable not only to Schrödinger, but actually to pseudo-differential operators, as long as the unperturbed operator is a constant coefficient or a Fourier multiplier. And the assumptions are very weak, so you just need to assume that this function is smooth and say polynomially bounded, and pick any lambda. So lambda is a regular value of t, which means that the gradient, so the gradient of t is never 0 when t of psi is equal to lambda. And then there exists a sequence of smooth potentials, Vn, such that possibly after rotating the coordinates, you have this upper bound here. And this is exactly what Ionesco and Jerison did for the Laplacian. So if t of d is d squared, basically, minus Laplace. So then this is just the Ionesco-Jerison example, but you can do it for any operator of this form, right? And then you see that if q is bigger than d plus 1 over 2, if you just sit down and calculate the LQ norm of this potential, you see that it goes to 0 when Q is bigger than d+1/2. Yeah, so this would be a counterexample, but only for embedded eigenvalues. Okay, and how one constructs the potential is very simple. You start with a guess for the eigenfunction, and then you just define the potential by this equation, and then it's a counterexample by construction. But the trouble with this approach is that if you take Z, which is not a positive real number, then it's hard to force this eigenfunction to be an L2, because these eigenfunctions usually have to form something like psi of x is e to the I x1 times another function which decays. And so if you want to do this for, so this would work for z equal to 1, but if you want to do this for z equal to 1 plus I epsilon, you would have to multiply this thing here by 1 plus I epsilon, and then of course you're no longer in L2. So this was sort of the obstacle here to immediately do this for non-real eigenvalues. And so instead of doing that, we went back to the original sort of way of proving the upper bound, the Germanfinger principle. And if you look carefully at this simple chain of inequalities, right, so there are 3 inequalities involved here. 2 of them are, there's nothing that you can do about them. They are sharp. So this is Hölder's inequality, and this is the Kenny-Gruis-Sock bound. So you can always make them sharp by choosing sort of the right potential here. But actually, you can lose something in this trivial inequality, right? This trivial inequality is very estimated the norm of the Germanfinger operator by 1 just from the knowledge that 1 or -1 is an eigenvalue. But actually, the norm may be much larger than its largest eigenvalue in modulus. So the largest eigenvalue modulus is called the spectral radius. So this inequality is potentially very, very bad or not sharp. Okay, so I'm just repeating some things that Sabine already told you in her talk, but I will be brief here. So what we did is we looked at basically the real part of this Germanfinger operator, or the self-adjoint part. And if you do a straightforward calculation, say z is equal to 1 plus I epsilon here, you find that the real part is something like this. So you have the, right, so here I'm assuming already, I didn't write this, I'm assuming already that v is equal to a characteristic function. So you have this characteristic function here on both sides, here and here. The operator is of size epsilon, and you have this approximation of the identity in the middle. So this is an approximation of the identity on the scale epsilon. Right? X is just the real part of the free operator, so minus Laplace -1. Okay, and now what have we gained? Well, because A is non-negative and compact, we know that actually the norm of A is equal to its spectral radius. So then this inequality where we said that we can potentially lose something is completely sharp for A. So if we take this this tube again, and we take chi to be the indicator function of this tube, or not quite, we have to blow up the tube a little bit, so take some large but fixed constant and just stretch this a little bit. And then you can show that, well, you always have the trivial upper bound, which is just, if you look at the formula for A, you see this immediately. And then making this M sufficiently large, you can prove that there's almost a corresponding lower bound. So A in norm is bigger or equal than 1 minus something very small. So this plus means plus epsilon for any epsilon. And now if we had the same lower bound, not just for the real part, but for the full Germanfinger operator, then we would immediately be done. We could show that the conjecture fails for Q bigger than d+1/2, because again, if you compute this LQ norm, then we see that this goes to 0 as epsilon goes to 0 in this regime. Okay. And also, we can compute this quantity here, which appears in the long-range bound. So this is the second result of Frank that I showed you. And so the counterexample also shows that this is sharp, right? That there's always an upper bound, and this example shows you that there's a corresponding lower bound. Okay, but unfortunately, the Germanfinger operator is non-normal, so its spectral radius may be smaller than its norm, but we can only estimate the norm. The spectral radius is very difficult to sort of get your hands on. So, however, we still expect that, based on the calculations that we did, that the Germanfinger operator is almost normal in the sense that, you know, the spectral radius should not be much smaller than the norm. Should be bounded by some fraction of the norm from below. And such an inequality would probably also imply other interesting lower bounds besides the ones that we proved. But again, so we could not prove this, and we used a different argument. So our argument mixes this previous construction, this constructive part, with a certain abstract argument, and this was explained by Sabine in her talk. I will not go into great detail here. Yes, so basically we can say that the potential, there exists a potential and it has certain properties, but we cannot really point our finger at the potential. So still certain non-constructive elements involved in this argument. All right. So now, as the title suggested, I will want to talk about sort of results that are known beyond this conjecture. So I already told you about this long-range bound here. So let me just recall the two bounds. So this is what I call short range, and this is what I call long range. So we are interested in what happens when Q is bigger than the threshold t+1/2. And as I said, our counterexample shows that this long-range bound is actually sharp. And there's also a local version of this bound, which goes as follows. So you can so if you leave the scale of LQ spaces and you allow an integral of the potential, so this is the critical exponent t+1/2, but you allow some exponential weight here, and the exponential weight depends on your eigenvalue. Then you can actually prove a bound like this. And why is this a local version? Well, because you see, if you take, so if x is much bigger than, let's say x minus y, sorry. So if this thing here is much bigger than 1 over the imaginary part of square root of z, then this exponential becomes very large and the contribution becomes negligible. So basically you only integrate over a ball. So we're integrating over x, so we're integrating over a ball centered at y with radius constant divided by imaginary part of square root of z up to some small error. So that's why I call this a local bound. And the counterexample that we constructed together with Sabine also shows that so all of these bounds are best possible. They're all sharp. And the question now is, when do we have improvements to these bounds, to these sharp bounds? So as I already mentioned, you can improve this when you assume that the potential is radial. So in this case, Frank and Simon proved that actually the Laptev-Safronov conjecture in this case is true. And also the restriction gamma is less than d/2 is best possible. And this follows from an earlier result of Sabine. Okay, but what about non-radial potentials? So here is another class of potentials that I've studied recently. I call this sparse potentials or separating potentials. So basically, these are just bumps that are isolated far from each other. On each bump, I have a potential, and basically they're so far from each other that they don't talk much. So we can expect to have some improvements in the bounds where we, instead of taking the LQ norm over everything, we just take the maximum of the LQ norms of each bump separately. Okay. All right. So here I'm assuming that we have finitely many bumps, but this can also be done for infinitely many. All right. So these are supported on this joint set, like in the picture I just tried to draw. And so the first theorem here is that yes, you can improve the previous bounds if your potential is what I call separating at scale eta inverse, which means that if you sum up all these numbers here, so Lij is a symmetric matrix. It's Kronecker delta plus the distance of omega I to omega j, right? So sparseness means that these are sort of separated. So if these are well separated at this scale, then you can prove that for every eigenvalue in this regime, so imaginary part of square root of zeta of z is bigger or equal than this scale eta, then you can decouple basically these bumps. So instead of considering the whole potential, you consider just one of the bumps, and the same for the long range inequality. And moreover, if you assume the stronger condition here, so instead of so you assume that these Lij have to decay even faster, because now you're not writing an exponential, just a polynomial of it, and you ask that this is finite for every epsilon, then you can actually get rid of this. You can get rid of this lower bound on the imaginary part of square root of z. So you have this this inequality here, for example, but then you need to restrict your Q to values strictly less than d+1/2, and then of course this inequality here, the constant depends on Q, and it will blow up when you want to go to d+1/2. Okay, and obviously the improvements for sparse potentials relies on sort of almost orthogonality of the individual bump functions. So now I'd like to talk about another improvement, and this concerns random potentials. So now consider, so let's take a fixed deterministic potential and randomize this at a scale h. So what we do is we take this sum, so we sum over a lattice of lattice spacing h. And so this is just the indicator function of a cube, of the unit cube. So at each lattice point, we multiply this potential with some random number omega j, and these are some random variables. These are mean zero Gaussian or symmetric Bernoulli random variables, and let's assume they're between -1 and +1. So in particular, you can think of an Anderson potential, where you replace v of x by some constant, some number vj here, and so this was the original motivation, but actually the whole thing works for this more general case. So the next theorem is still in preparation, and this is joint work with Konstantin Merz, who is also in the audience. So, okay, this is sort of a preliminary version, which says that there are constants, so independent of anything, so just a number m0 and a constant c, such that the following holds. So you have three parameters here. You have r, lambda, and you have h. Okay, h is this randomization scale here, and r is the support of the potential. So we are assuming in the first step, we are assuming that the potential is not only in LQ, but it's actually supported on a ball of radius r. This might seem like a very strong assumption, but if you look at the inequality, you will see that this R is almost absent. So it only shows up logarithmically. So this is sort of, you can almost take the limit up to this log here. So you have these three scales, R, lambda, and H. And of course, H needs to be less than R because R is the support of your potential. So there's doesn't make sense to randomize on a scale bigger than the scale of the potential. And then there's also this epsilon here, which basically has the meaning, so what I already explained, that we focus on regions in the plane in some sector here, right? So we're not interested in things that happen outside a small sector, because for those eigenvalues, we have much better elliptic estimates. Right, so we assume that this epsilon is much smaller than lambda. And importantly, we are assuming here that Q is, sorry, I want to use this. Right. So basically Q is twice as large as before. So remember, the critical exponent was d+1/2 in the deterministic case, and now we can go to double that. So we can look at potentials that decay at a much slower rate at infinity than in the deterministic case, twice as slow. All right, and so for any m bigger than this m0, each eigenvalue satisfies such a bound. Okay, so this is just by scaling, and then so this logarithmic loss here is more or less negligible, and then there is some loss in H, and I mean this is understandable that if you make H very large, then you make the randomization very weak, then this bound becomes weaker, right? And so, okay, this holds for all omega, except for an exceptional set, and this exceptional set has measure at most e to the minus constant to the power m squared. So if you take this m here big, then this exceptional set will have very small measure. Okay, so the conclusion with regards to the counterexample that I discussed before is, so if you plug in the potential in the counterexample, you can calculate that if you randomize on a scale which is smaller than this scale here, then this counterexample is almost surely destroyed. So it's not a counterexample anymore. Right, so this counterexample was a characteristic function on a long thin tube, and basically if you put pluses and minuses here randomly, then this cannot be a counterexample anymore. That's what this says. And the improvement in the random case relies on what's called square root cancellation. So the fact that you can go from d+1/2 to double that d+1 is what's called square root cancellation. And also, the compact support assumption can be removed at the price of a tiny bit of pointwise decay. So this is a more or less an immediate corollary. So you fix delta, and you assume that your potential now is in not only in LQ, but it decays a little bit. So it has some pointwise decay. And then you can replace, so see here, there is no R anymore, there's no logarithmic loss, but we paid with this weight here, right? And the lambda here just comes from scaling. So this is, all these inequalities are dimensionally consistent. They're scale invariant inequalities. And again, this holds for all omega except for a set of small measure. In fact, we expect that this statement remains true for delta equal to 0. So we expect that we can get rid of this pointwise decay here at the price for making strict inequality here. All right. And let me also mention that there are some recent results of Safronov, who considered eigenvalue sums, not individual eigenvalues, for random Schrödinger operators of this type with complex potentials. However, these results don't say anything new about individual eigenvalues beyond what is already known from Rupert Frank's deterministic results. So this is sort of a different thing here. All right, so let me briefly sketch the proof of this of the first part of this theorem. So what you do is you can always reduce yourself by scaling to considering a real part of set equal to 1. And then because you're in a sector, you can always assume that this imaginary part is very small. And so if the Born series, so by the resolvent identity, you know that if this Born series converges, then then the resolvent of the perturbed operator exists, so Z cannot be an eigenvalue, right? And this converges exactly if the this converges if the spectral radius of this compact operator R0 times V is less than 1. All right, so now let's look at one such piece here. So R0B to the power n, and you write this as a multilinear expansion. So you take V's here, Vi1 up to Vin, and each piece is supported in a ball of radius 2 to the j. So this basically amounts to a dyadic decomposition of the potential. And then so therefore you can always reduce to the compactly supported case, right? So you only need to prove the compactly supported case. And then the next thing to observe is that, you know, there are various ways how you can write this this expansion here, right? So you have you can write this as R0 square root and then a V and then another R0 square root and so on and so forth. Right, and you only have some, I mean, you cannot do this globally, but sort of at the boundary of this expression, you might have some lonely pieces which don't factorize like this, but they don't play a role, because at the end we're going to pull the nth square root of this. So anything that doesn't come, that just comes a bounded number of times will just be annihilated to 1. So so most of these pieces can be written like this, and that's enough. So we consider such pieces, such building blocks, so to say, and because we are localized in X space now, so this is because we are assuming that the potential has diameter 2 to the j. By the uncertainty principle, we can smooth in Fourier space, so we can smooth this Fourier multiplier square root of R0, which I denoted by this C delta. So C delta means some generic Fourier multiplier satisfying such an inequality, right? So localizing on a scale R allows us to smooth out on the inverse scale in Fourier space, so we can always assume that the resolvent satisfies, or the square root of the resolvent satisfies this upper bound. And then it remains to prove that these blocks that we have, that the L2 norm of these is bounded by something which is strictly less than 1, because then we know that the spectral radius of the whole thing is less than 1. Again, for everything, for every omega except for some exception set. And then by standard large deviation estimates, it's sufficient to prove this in expectation. Okay, and now we have another localization. So this time we have a localization in Fourier space, because we are only interested in sort of a small neighborhood of the unit sphere, because that's where the characteristic set of our operator is. So we're considering minus Laplace minus 1. So this is an elliptic operator outside of a small neighborhood of the unit sphere. So we localize in Xi space, which means that we can basically discretize in coordinate space. So I write this in parentheses because I won't make this precise, but there are ways to make this precise. So then we can basically assume that the potential and so all the other operators, they basically live on the lattice, on the standard cubic d-dimensional standard lattice. All right, and then also we can replace these resolvents or half powers of resolvents by something which is known as a Fourier extension operator, basically by averaging over dilations, and we also average over translations to sort of go from RD to ZD. Again, I won't make this precise here, but so this is what one has to do, and then one can reduce this this inequality here to an inequality on this Fourier extension operator. Here I just wrote what it means to take the norm of this. So we take the scalar product here, and we take the sup over all G1 and G2, which have norm 1. Okay, and E, as I said, is sort of a discrete version of the Fourier extension operator, and I won't write this down here. And we can assume that V omega basically lives on a lattice, or in other words, it's constant on the unit scale. Okay, so now the next step is we want to replace this sup over an infinite set by a sup over a finite set, and we pay for this by what is well, usually called an entropy cost. And then the sup over the finite set can be estimated by standard probabilistic tools such as Dudley's inequality. On the other hand, the entropy cost can be estimated by a clever idea of Bourgain, who used this in a slightly different context. So he was interested in existence and completeness of wave operators, but the techniques work very well for eigenvalues of Schrödinger operators with complex potentials. And in all of these estimates, one uses the steintomas inequality, or sort of a discrete version of the steintomas inequality. So let me show you the entropy estimate that goes into these bounds. Suppose we have a linear operator S from a finite dimensional Hilbert space H to some other finite dimensional space, not a Hilbert space, but here it's an L infinity space on M elements. And so we are interested in this number here, which is called the covering number. So this is the minimal number of balls in L infinity of radius epsilon that we need to cover this set. So the image of the unit ball in H. Okay, and so there is an entropy bound proven by these authors here. And Bourgain, in one of his papers, shows that actually this entropy bound can be written in this form or estimated by this quantity. So the logarithm of n is bounded by something like this. And the important thing is that the dimension of H does not appear in this upper bound. So you can basically you know, the assumption that the Hilbert space is finite dimensional is more or less irrelevant because the bound is independent of this dimension. So you can always get rid of it at the end of the day. And in our application, this operator S is the discrete version of the Fourier extension operator. And using this entropy bound, you can control this this entropy cost here, and you compute this sup, and so knowing the sup over finite dimensional set plus paying the entropy cost will get you where you want. Okay. So to finish, let me say something about open questions in this business. So it would be interesting to know whether the Laptev-Safronov conjecture is true sort of generically. I mean, in some non-random sense, we already showed now that for random potentials, this is almost surely true. But it would be interesting to find some generic condition on the potential that prevents these kind of long thin tubes, which are known as NAP examples, at many scales. And the expectation is that probably something like wave packet decomposition will play an important role. So this is a tool that is used by harmonic analysts, basically as a standard device. And what it does, it decomposes a function into infinitely many NAP examples. So this would sort of be a natural device here. And related to that, it would be interesting to know if one can use superpositions of these NAP examples to produce potentials that have many eigenvalues. So our counterexample only gives us one eigenvalue, but so there are other interesting questions about sums of powers of eigenvalues and numbers of eigenvalues, and to prove that these results are sharp, one would need something with a superposition of these examples that give us many eigenvalues. And again, coming back to this spectral radius, one probably needs to understand the spectral radius of the Berman-Schwinger operator better in order to do this. Okay, and so I explained what the steintomas theorem is, or inequality, and basically everything I talked about, all these upper bounds, they depend on this, they rely on this steintomas inequality, but there are much more sophisticated tools in Fourier restriction theory that have not been used yet in spectral theory, and it would be interesting to know if one can use these more modern and advanced tools as well. In particular, in the random setting, Bourgain, in one of these papers that we used for the previous result, there he speculates that one could use perhaps the sharp two-dimensional restriction theory, which is also known as the Carlson-Chiolin theorem, to actually reduce the decay assumption from L3 to L4. So in 2 dimensions, right? If in 2 dimensions, this d plus 1 is equal to 3. So this is what we get with this construction I showed you, and 4 would be what you get by using the Carlson-Chiolin estimate instead of the steintomas estimate, and this would be sharp, and this would be natural and sharp. And the question is this true? Thank you very much for your attention.
So we can all thank the speaker. And well, whoever has question feel free to participate.
Thanks, Jean-Claude, for the talk. So when you do the probabilistic argument, you end up having this that these potentials satisfy this stronger inequality, except for omega in a set of some small, quantitatively small measure, right? Mm-hmm. So is the size of this set of small measures sharp? Do you actually find a set of positive measure?
Good question. We don't know. And then also I don't know how to prove this. But that's a natural question. We don't know this.
Mm-hmm. And could it be? I mean, I guess you won't know either if you didn't know for the first question, but presumably the size of this set could depend on Q as well. Maybe, for instance, for
yes, I suppose it will. Mm-hmm.
And I would expect, say, for Q in some right range, it might be even measure 0 or something like that.
Yes, but you know this constant, you know, this little c, because we're looking at Q in a compact interval. We mm-hmm. can sort of choose the small c once and for all for every Q the same, right? We just take the worst. So in this inequality, actually, c is little c doesn't depend on Q.
Mm-hmm. Yeah.
Because we're looking at the compact interval here.
Okay, so c is a continuous function of Q. It's something that depends continuously on the parameter.
Yes, exactly.
Okay, good. Thanks.
Okay, so does someone else have a question? Well, in that case, I think we can probably thank the speaker again. And well, we will meet again next week for a talk of Yann Chauvet, and it will be the last seminar of this year. Oh, thank you again.
Thanks a lot, Jean-Claude.
Thank you very much.